Good morning, all of you TyBsc physics student. We have to see here our subject is solid state physics, and we want to continue the fourth chapter, which is the magnetism. In this chapter, we have to continue the next point, which is known as the anti-ferromagnetism. So consider, before see the point of the anti-ferromagnetism, we have to see here what is the ferromagnetic material. And last lecture we have to already see that what is mean by ferromagnetic material. That ferromagnetic material which is considered as the material which has shows the magnetic property, and that material we have pick up the iron pieces of the material, and that material we have show the property which is below the Curie temperature or low temperature range. And if we consider as above the Curie temperature, that material which has show the paramagnetic property, and that we have to see in the figure is A. So that shows the ferromagnetic property, and that alignment of spin direction which is upside of the characteristics. So that is shown by the material we have containing the characterize that two interlocking sets of the atom or grouping of atom, each which has two spin lining up character of ordinary ferromagnetic substance. Two lining up characteristics of the spin lining that is considered as here. So that show the spin direction which is up direction. So that material which is considered as the ferromagnetic substance. Suppose if we consider some of this material we have to continue see here. So that material considered as the two sublattices, and they are called tends to the magnetize in the same direction. So that material which is considered as the ferromagnetic material. So we have to see here that two sublattices, so that have oriented in the upside direction, that is which is in the same direction. So that type of material which is see in the figure A, so that is considered as the ferromagnetic material. And in some of the material like magnesium oxide, that is MnO, the two sublattices have identical magnetic moment but opposite in direction. So what here, the two sublattices have identical moment but opposite direction, that is shown in the figure B. So consider here, so that one of the spin which is upside direction and one of the spin which is downside direction, and magnitude of this vector which is same. So this type of the orientation which is due to the exchange of interaction force between the adjacent atom, exchange of the interaction of force between the adjacent atom to show the anti-parallel spin orientation, the spin of orientation which is considered as the anti-parallel. And this material which has show very little external magnetism, so that material which is considered as the anti-ferromagnetic material. And if this material which has heated significantly or sufficiently material, so if we increase the temperature of this material, that ferromagnetic material, which is this material we have show the property of the paramagnetic material. So that types of the material which is considered as the anti-ferromagnetic material. And in the next figure we have to see that the ferrimagnetic material, the spin alignment orientation of this material which is similarly as the anti-ferromagnetic material, but the magnitude of one of the spin alignment which is as compared to anti-ferromagnetic material as it is small. So this type of sublattice orientation of the material which is considered as ferrimagnetic material, and that material we have to consist two sublattices which are not identical. in the ferromagnetic material and antiferromagnetic material, that alignment of the spin orientation which are same magnitude and identical, but in ferromagnetic material, so that sublattice which are not identical, and there is a net effect which is similar to the ferromagnetism but considerably weak effect. So, and the name of this phenomena which is considered as the ferrimagnetism, and the substance which processing it are called the ferrite. So that material which is considered as the ferrite material. So what is we have to clear that idea. So that material which is according to similar as the ferromagnetic material, but we have to consider that magnitude which is low. So this material which is called as the ferrite, and example of this such as nickel ferrite. So that is considered 2 ions have the nickel, and 3 ions of the ferrite. So that is material which is considered as the nickel ferrite, and that exchange of interaction locks into ion into a pattern like we have to see here the figure that is the ferrimagnetic material. So in ferromagnetic material, the same anti-ferromagnetic exchange interaction exists, and which align in the magnetic moment which is anti-parallel, and since ions are different magnitude of magnetic dipole moment, and that magnetization is not zero in this the material. And in ferrimagnetic material we have to consider, so above property we have to show here the ferromagnetic material. So that ferromagnetic material, that anti-ferromagnetic exchange of interaction exists which align in the magnetic moment anti-parallel. When anti-parallel, that material which is considered as the anti-ferromagnetic. If ferromagnetic, that alignment which is the same direction in the upspin, and in consider in the ferrimagnetic material, that also exchange interaction disappears if the material is heated above certain Curie temperature, that is the characteristics temperature, and that ferrite are crystals which have small electrical conductivity as compared to the ferromagnetic material. So that property, that small electrical conductivity as compared to the ferromagnetic material. Next point we have to see here the Néel temperature, and that Néel temperature denoted by the Tn, that is capital T suffix n, and this temperature above which and the anti-ferromagnetic material becomes a paramagnetic. So what property show that anti-ferromagnetic material which have, if and what type, so that if we increase the temperature, so that anti-ferromagnetic material which have show the property of the paramagnetic material, and that is the thermal energy becomes large enough to destroy the macroscopic ordering within the material, and it is also called the magnetic ordering temperature. So this temperature which is considered as the Néel temperature. So that what is meant by Néel temperature, that Néel temperature which is considered as the anti-ferromagnetic material, if we increase the temperature at certain amount, so that material which is shows the property say as the paramagnetic material. So such temperature which is considered as the Néel temperature, and this Néel temperature which is analogous to the Curie temperature and for ferromagnetic material, and it is named after the Louis Néel, and who received the Nobel Prize in the 1970 in the work of the physics area. So if we see the table that indicate that the Néel temperature of several antiferromagnetic material, so that substance which is considered as MnO, and Néel temperature range which is 120 T, MnS which is considered as 165 temperature in Kelvin, and there are the different example which is the Néel temperature value of corresponding antiferromagnetic material is there. So next point we have to see here, so that ferrite material which is seen the property. So what is the application of this ferrite? So that ferrites are the class of the ferrimagnetic ceramic chemical compounds of consisting of the mixture of the various metal oxides. So that we have to see already that component which is C oxides and sulfurs which is also in there there. So that's why we have to see that the mixture of the material, we have to see here the various types of the metal oxide, and this is usually including the iron oxide and their general chemical formula, which may be considered as Ab2O4, and where A and B represent the different metal cation. So A and B, which is show the different metal cation, and O is the oxides. For example, consider here ZnFe2O4, that is zinc ferrite oxide. After that COFe2O4, that is cobalt ferrite oxide, and MgAl2O4, that is magnesium aluminum oxide. So these are the ferrite, which is usually non-conductive ferromagnetic ceramic compound, and which is derived from the iron oxide. And such as hemite, which is considered as the Fe2O3, or magnetite, which is Fe3O4, as well as the oxides of other metals which is used here. So in terms of this ferrite, the magnetic properties depends on the magnetic properties. These ferrite, which are often classified into two types, main types, that soft and hard ferrites, and which has refers to their low or high coercivity of their value. And that two types, that soft ferrites and hard ferrites. So first type, which is considered as the soft ferrites, and these soft ferrites that consider as the low coercivity are called the soft ferrites. So that we have to see in the hysteresis loop what is mean by coercivity and what is mean by the retentivity. So that depends upon this coercitivity value. So that ferrite, which is known as the soft ferrites, or if we consider in this soft ferrite, so what is mean by the coercivity? So what is mean by coercivity? That coercivity, which is mean by simple, the magnetic field intensity H, magnetic field intensity H value, which is reverse in the hysteresis loop. And if we consider that magnetic field intensity is reverse, the flux of the material which is becomes zero, flux of the material which becomes zero, and this point which is called the coercivity. And that if we this coercivity value which is low, that is means by, so that is the magnetic field strength value 0, and material is demagnetized, or removing magnetized value in the material. So that is mean by the coercivity, and this low coercivity value which is called as the soft ferrite. And this ferrite that are used in transformer or electromagnetic cores containing nickels, zinc, and more manganese compound. And these are the low coercivity, means that materials magnetization can easily reverse direction without dissipating much energy, which is in the hysteresis loop, which is also already seen in the last lecture. And while the material is high resistivity prevents the eddy current in the core and another source of energy which is loss, and because of this comparatively low losses at high frequency and extensively used in the cores of the RF transformers. So that material soft ferrite materials which is used in the transformers and inductors in the applications such as the switch mode of power supply. And common uses of this soft ferrite, which is material considered as the manganese zinc, which are formula MnZn, and the formula which is considered as MnAZn 1 minus A Fe2O4 are the general formula. and consider as the nickel zinc, that is NiZn with the formula NaZn1 minus A Fe2O4, and nickel zinc ferrite, which has the exhibit higher resistivity than the manganese zinc, and therefore the more suitable of the frequency above 1 megahertz, and manganese zinc, which is considered as the higher permeability of the saturation induction than the nickel zinc. So next type of, so that is considered as this soft ferrite material, which is used in the transformer and conductor material. And next type of the ferrite, which is considered as hard ferrite, and this ferrite, which is considered as compared to soft ferrite, so high coercivity value and high remanence after the magnetization are called the hard ferrites, and the permanent ferrite magnet are made up of the hard ferrite, and these are the compound of iron and barium and strontium oxide. So if we see that material which is magnetically saturated state, they conduct the magnetic flux well and have the high magnetic permeability. So this is the enable called the ceramic magnet, and to store the stronger magnetic field that iron itself. So if we see the value of the considered magnetic value B, which is considered as 0.35 Tesla, and the magnetic field strength, which is about 30 to 160 kilo ampere per turns per meter, and which is considered as 400 to 200 oersted, that magnetic field value is there, and the density of this ferrite magnet, which is considered as 5 gram per cubic centimeter. If we consider the structure of this crystal structure of the ferrite, which is considered as the cubic ferrite, which has the spinal crystal structure, and ferrite, which is add up a crystal morphite consisting of the cubic closed packed structure, and which is considered as the FCC and oxides O2 minus iron, and a cation of occupying 1/8 of the octahedral holes, and B cation, which is occupying the half of the octahedral holes, which is see in the figure, and the magnetic material, which is considered as ZnFe, has the formula ZnFe2O4 with the Fe3 plus cation, and occupying the octahedral site and half of the tetrahedral site, and the remaining tetrahedral site is the spinal are occupied by the zinc 2 material. So this different material we have to see in the figure, so we have to got clear that idea. So how is the nature of the type of the material? First, which is considered as in this material, we have two types of the cation, and third one is the oxide. So for A cation, which is considered as the big pair of the A and small pair of the O, so that is cation and oxide pair. Which is for B cation, which is considered here big pair of B, which is of the center, and surrounding of this oxide is there. And next figure, which is considered as the structure of the mineral spinal of MgL2O4. So that is the mixture of compound of the cation A and B and oxides. So this is the structure of the ferrites, and we want to continue here. So this, what is the application of this ferrite, which is here? So we have to see here the application. Consider of first application, that ferrite core are used in the electronic inductors, transformers and electromagnets, and these high electrical resistance of this ferrite leads to the very low eddy current, which is losses in the device. So these are important application. Second application, which is considered as the ferrite are commonly seen as a lump in a computer cable called as a ferrite bed, and with the help of this prevent high frequency of electrical noise, that is radio frequency of interference, and from existing or entering the equipment that ferrite also use in a broadband transformers. Now next application, which is see here, that early computer memory store in the data in the residual magnetic field of hard ferrite cores, and which were assembled into array of the core memory. Next, which is one the ferrite powders which are used to coating the magnetic recording tapes or tape recorders. Next one, which is considered as the ferrite particle, also used to component of radar absorbing material or coating used to the stealth aircraft, and the absorption tiles lining the rooms used for the electromagnetic capability measurement, etc. Next one, which is considered as the ferrite magnet, are used in the loudspeaker. And last one, which is considered C as the it is common magnetic material for electromagnetic instrument for pickups, because of the price of relative high output, such as pickup lack certain sonic quality of found in the other pickups, such as those that use the alnico alloys or more sophisticated magnet. So these are the application of the ferrite. Up to this point, so our fourth chapter, which is magnetism, which is over or complete. Now next lecture we have to see here the third chapter, which is most important chapter, which is considered as the free electron and band theory of the metals. So thanking of you.